Okay, now look at the third case about the double integral on non-rectangular region. You can see I mentioned here the third case happens when the region R can be described in the forms of the first case and second case both. It means the region R can be described in the form of case 1 and 2 both. So in this case we are allowed to switch the order of integration, and when we switch the order of integration we might get easier integral to solve. And remember, sometimes some double integral in the given order might be very difficult or even impossible to solve, but when we switch the order of integration, then the evaluation might get easier or possible, the evaluation of the double integral. Regarding this, look at this example of page 23, which is very interesting example. You want to calculate the double integral of this function. It means f of xy equals sine x over x on region R. Okay, look at region R. So look at here. You may describe the region R, for example, in the form of case 2. When we say in the form of case 2, look at here. Here x is 1, so here y is 1. So in the form of case 2, I can say y is from 0 to 1, okay, and x is from left bound, which is y, to right bound, which is x equals 1. So I can say y is from 0 to 1, x is from y to 1. Okay, let's set up the integral in this case, in this form. See what happens. So I have the double integral of sine x on x dA on R. So if you remember, we described the region in the form of case 2. So if you remember, we said that x is from y to 1, x is from y to 1, and y is from 0 to 1. Sine x over x. Okay, according to this will be dx dy. Look at here. Y is from 0 to 1, x is from y to 1. So we can see here. Y is from 0 to 1, x is from y to 1. X is from y to 1. Okay. Now let's try to calculate this integral. Okay. So you can see, first we have to calculate this integral with respect to x, right? First with respect to x. So it means we have to calculate this integral, the integral of sine x over x with respect to x. But we know that, if you remember from calculus 1, some function like this, sine x over x, like my point is, with some analytical method that we know, we cannot find an antiderivative for this function. So we cannot find an antiderivative for this function. So it means this integral sine x over x dx cannot be solved. So we cannot find the answer to this double integral. So what to do? Here is the point. That look at the region again. This region can be mentioned, the region R can be described in the form of case 1. It means, okay, I can say x is from 0 to 1, y is from 0 to x. So according to this description, we can switch the order of integration. So one more time, I repeat, I can say it means we are going to describe the region R in the form of case 1, so accordingly the order of integration will change. So I can say x is from 0 to 1, then y is from 0 to x. X is from 0 to 1, y is from 0 to x. Right? Like this. Okay, like this. So we can switch the order of integration according to the description of region R in the form of case 1. So we have sine x over x. Okay, look at here. This time we can say y is from 0 to x. X is from 0 to 1. So here we have, you can see we switch the order of integration. dy dx. dy dx. So you can see here we describe the region in the form of case 2, so the order is dx dy. Then we can describe the region in this way, in the form of case 1. Yes, in the case 1, which is, we can say x here. X is from 0 to 1 and y is from 0 to x. Okay? So according to this description, dy dx. Now, first with respect to y, then with respect to x. Now this integral is solvable. So let's go ahead. Here. So we have integral from 0 to 1. This is for x. So actually, look at here. This the first integral is with respect to y, right? So this sine x over x for the first integral is just like constant. So you can move this one out of this. You can bring this one here. So I can write sine x over x times the integral from 0 to x dy dx. So you can see this sine x over x for this integral, because it's with respect to y, is a constant. So you can take it out of this integral. It's just like a scalar. So let's calculate. So we have integral from 0 to 1 sine x over x. Now look at here, the integral dy from 0 to x equals what? This equals y from 0 to x, right? Okay, let me put bracket here. So here we have dx. Okay, so you can see this integral. The integral dy is y from 0 to x. Okay. Since the space is not enough, let's continue the calculation here. Okay, let's continue up here. Okay, so it left this one, right? Now, so this equals integral from 0 to 1 sine x over x, and here the value of this when y equals x minus when y is 0. So we have when y is x, it means x minus 0. dx, right? When y is x minus when y is 0. And look at here, this equals x. And this x simplified by this x, right? These two. So it's left, let's move on here, integral from 0 to 1 sine x dx. You can see when we switch the order of integration, we can solve the integral. So now this is easy. What is the integral of sine x? The integral of sine x is minus cosine x. Minus cosine x from 0 to 1. Okay, 1 radian, okay. So we have minus cosine 1 radian minus cosine 0 cosine 0. So this equals minus cosine 1 minus cosine 1, and look at here, cosine 0 is 1, so minus plus 1. So this is the answer. So minus cosine 1 and cosine 0 is 1, so minus 1. So the answer is minus cosine 1 radian plus 1. So you can see when we switch the order of integration, we can solve this integral.